Welcome everyone. I'm very glad that we have Andrea Tagliasacchi here from Google Brain Toronto. He's a senior researcher there working in the office from Jeff Hinton. And he has done a lot of influential work on 3D and 4D reconstruction. And very recently won the Best Student Paper Award with his collaborators at CVPR 2020. So we are very much looking forward to your talk.
Right. Thank you, Andreas. So this actually was a talk that I gave in part at CVPR. So I'm gonna basically represent it here. It was actually part of this 3D scene understanding seminar that happened there, and I was using actually part of the description of their workshop to kind of justify the papers that I was going to talk about. So they were talking about scene understanding, and they were discussing how they rely on the ability to parse the environment, to reconstruct the environment, and to interact with the environment. And basically, the three papers that I'm going to present today fit in these three categories. So I'm going to start by describing a technique that is able to essentially parse a scene via I'm posing an hypothesis onto the scene and then refining it through iterations, and this will be clear in a second. I'm gonna then move on to reconstructions of scenes, but more in terms of digital humans, reconstruction of digital humans from a new perspective that might be familiar to some of you. And then the third part is we kind of tried to come up with representations that are not just friendly for computer vision and for acquisition in the wild, but also for computer graphics or traditional computer graphics, where there is no need for an explicit translation in between the two representations. So I'm going to start from the first paper. This actually was a poster, sadly, at CVPR, because I think it's actually a very neat technique. It's called ACNe, Attentive Context Normalization. Yes, you work on points. Yes, I wanted to have an image of pimples being aligned with each other, but I couldn't find one on the internet. And it's about permutation equivariant learning. So what does that mean? So permutation equivariant learning regards problems of this form. So I have an input tensor, which is actually an potentially unsorted set, right? So in this case, you have this collection of unsorted points P1 to Pn. And what happens is that because this is a set, if you change the input order, you expect the output to change accordingly, right? So if I permute the input, you expect the output of the network to permute in exactly the same way. And whatever network you have in the middle, in this case, it's just a simple MLP, is supposed to guarantee this property, right? And you agree with me that if the network in between this input and outputs was an MLP that acted on every single point individually, you will have this characteristic, right? Because if I change the order on the input, it just simply permutes the output as well. So now you ask yourself, the question is like, why do we care about these problems where you want to have permutation equivariance rather than permutation invariance? Well, the answer is that if, for example, you're solving a robust least square optimization problem, where you want to have a collection of square residuals with these weights Wn, and you can see my mouse, by the way, right? I'm asking.
Yes.
Yes, you can see my mouse. So if you have some terms over here that depend on these input quantities P1 to Pn, and then you have some weights in front of each of these terms, then it's clear that the Pn residual should be correlated to the Wn weight, right? So they're supposed to match each other in terms of learning. So the idea is that, for example, if you want to solve a least square optimization problem for which you have some ground truth solution, as you know, you can backprop through optimization, which means that this operation is actually differentiable, which means that now you want to have a network in this case that, given the collection of quantities in input, generates the weight that, when combined in this least square form, gives you the correct solution, right? So you can think of this as being in the first form as a form of robust optimization, where you want to figure out the weights to plug into the system to be able to get the right solution that you want. So what kind of problems belong to this class? Well, all right, there was this animation. Normalization acts in this class. So if now you think of P1 to Pn as being features within a network that doesn't really care about the order, then W1 to Wn actually are the normalization quantities for this network, and we'll see that in a second. Or it could be parametric fitting, right? So if I give you a bunch of points and you want to find out the the line that fits the points in the best way, this can be casted, as you know, as a ransack problem, or it can be casted as a robust least square optimization problem. And both of these problems basically aim to identify a subset of the input points in such a way that if I solve a least square problem for those points, and in the case of ransack, it's typically ideally conditioned in the sense that if I have n degree of freedom, I want n constraints. In the case of robust optimization, is an over-condition problem. And if you find basically the right points that you should pay attention to, you're gonna get the right solution. And a third problem, which is kind of our production problem, is stereo matching, right? So where you're given putative correspondences, and these are generated by whatever system you want. It could be just shift matching, or it could be like some form of deep matching. And you want to determine which one is the subset of features that match, and which putative correspondence should be discarded because they were actually outliers. So in this case, for example, in these first two cases, the points P1 to Pn were literally the points that you see on screen. In the third case, P1 would be a 4D vector, right? It will be the 2D coordinates of a pixel on the left image and the 2D coordinate of a pixel on the right image, right? So it's a generalized concept of point. So point as in the term of points, multidimensional point set. So now I'm gonna explain to you why does this work and what was the idea behind it. So start from the previous case that I had on the previous slide, these feature normalization that you have down here, right? So consider it in this following form. If I want to compute a feature normalization, what you want to do is that you want to remove the mean from the features and divide by the variance, right? So this is pretty classical normalization layer in your network. And it turns out that you can actually write the computation of mean and variance in least square form. And here I'm going to focus on the mean only, right? So if you write the computation of the mean mu of a set of features Pn in least square form, this is the expression that you get. And if you take the gradient and you vanish it, you're going to get the arithmetic mean as you know, or as you might have done in an linear algebra course. So now what happens is that if your point Pn, like in the image on the right, do not only contain a single distribution and no noise, right? So what happens is that this problem has a trouble in converging or giving you a meaningful solution. So for example, the mean mu of the point set that you're on the right is this red point that you see right here. And the reason is because this optimization problem assumes the Gaussian prior and no outlier prior on the distribution that you have in input. So there is ways of getting around this, and it's actually pretty simple. So you drop this assumption that you have this square constraint. You replace it by something that in statistics is called estimator. In computer vision is called the Rust kernel, and I'm sure there is some other field where it's called in some other way. But basically, you have this function k, which is typically a radial basis function that is monotonic. And basically, what you can do, you can take another step and you can convert this optimization problem, which is now non-convex, okay? Because the function k is not either a least square energy or on a L1 energy. And what you can do is that you can convert it back into an iterative form, right? So these are called iteratively reweighted least squares problems, or IRLS, because it's hard to pronounce it. And the idea is that you replace this single shot kind of estimation of the mean given your input constraint into an iterative one. So you start from an initial guess mu0, which is the guess of your initialization, basically, of your iterative solve. And then what you're going to do is that you're going to update the weights Wn to converge to your solution. So I'm not going to spend a lot of time on the structure of, these weights Wn, they need to be computed with respect to the current solution mu_t, but I'm not going to go into details. If you want to look at IRLS, I can point you to some good resources that shows you how to do this. But the idea is that if you now take the example on the right, I'm going to take the blue point as a starting point, and if you solve this problem, this is what happens. So basically, the initial condition basically converges toward a local solution that actually expresses what it thinks it should be, right? So it's basically able to ignore multimodal nature of your data set and basically lock into a particular solution that it likes. So, and this is pretty interesting, because if now you think that the image you're seeing on the right is a bunch of features, for example, that your network is supposed to work on, and maybe some of those features are just outliers and should be discarded, it means that adopting a solution like the one that you see in the equation on the bottom left should be able to allow you to converge to something that normalizes your feature against something that you care about, right? So you give at least the chance to the network to do so. So let's do exactly that. So we're going to go back to our permutation equivariant problem, which, as we said earlier, was fully differentiable in terms of the network that computes this weight W. And what we're going to do is that we're going to replace it with something that looks like an RLS optimization, right? So we're going to have this first block. This first block is an MLP. And by design, it guarantees permutation equivariance, right? And what we're going to do is that we're going to take our IRLS recipe and we're going to emulate it. So the first block, this MLP in input, is going to basically generate the collection of weights at the 0th iteration. So it's going to generate basically the initial configuration of the weights. And then as we go deeper within the network, every application of this ARB block is basically supposed to update the weights WN that represent the current state, right? So you're unrolling the RLS optimization step within a network, and the updates of the weights WN happen as you go deeper and deeper in the network. Does it make sense for now? If you guys have questions, please don't feel shy in asking. And yeah, as I said, like this network over here is an MLP, so it guarantees equivariant by construction, right? And what we're going to do next is that we're going to make sure that we guarantee equivariant throughout the entire system. So for example, this ARBA block is actually nothing complicated. It's called an attention residual block because you have this residual connection over here. Remember, the size of the input F and the output F is the same. That's why you can do this skip. And in here, what you have is the typical structure of a ResNet, right? So you have not just a single residual block, because otherwise that will collapse to basically be doing nothing interesting with the same reasoning that ResNet use. And then internally, again, you're going to have more MLPs, which again guarantee equivariance. And you're going to have this ACN block, which I'm going to open up in a recursive way. So we're going to look at the ACN block right now. And the ACN block is actually, don't get mistaken by the diagram, is actually extremely simple, right? So I'm actually gonna show you the equation first. So the ACN block is this green block, okay? And the only thing it does, it takes your features, it removes some mean computed on the features and divide by some variance computed on the features, right? And the only difference from instance normalization or context normalization, which are this operation without the W, is that rather than computing the straight mean and the straight variance or the normal variance of a set of features, it computes a weighted mean and a weighted variance of the feature, okay? And these weights W are computed by the network, right? So you're gonna train these two blocks, which is basically a weighted, the weight computation, basically. They're gonna receive an input, the features, and they're gonna output these vector W global and W local, which then get assembled to compute basically this weight W, right? So nothing complicated. We're basically asking the network to receive an input a bunch of features and decide which of the features are important and which not, right? And we use two different mechanisms to determine which ones are important and which not. One of them is, yet again, another MLP, so nothing special. So it takes a single feature in input and outputs whether he likes it or not. And the second one is essentially a mechanism that allows different features to talk with each other in a permutation equivariant way, which is achieved by a softmax. So softmax, if you change the order of the input, the output remains the same, therefore it guarantees the equivariance again. And then the only thing that we do is that we take a pointwise multiplication in between these two attention mechanisms to assemble the weight W that will normalize the feature. So as you see, it's extremely simple, right? If you remove the global one, this means that you're computing a weighted mean and a weighted variance where the weights are determined by an MLP, nothing else than that, right? And of course, these elements in white over here are learnable.
You must also, quick question. You must also be normalizing W to be between 0 and 1, or is there a normalization step?
Yeah, of course.
W?
Yeah, you normalize it to, So I guess there is different variants you can use, but yes, you would want it to at least be, yes.
After the multiplication.
After the multiplication, you can, there is, as you know, is like, these are choices that you make during hyperparameter tuning. So you bring all configurations, you throw them at some hyper-optimizer, and then it will tell you what to do. Okay. But yes, we have freedom to do both. And yes, normalizing to a unit distribution within the set is pretty common. Yes, good question. So now, before I move to this is it. By the way, the technique is it. Right? It's a bunch of MLPs, and the only complexity is basically the computation of a weighted mean and a weighted variance. So now I want to move to applications to show you a couple of different ones. And I kind of like to show reviewer number 2 because it's historically the one that attacks you. And I think that I guess this was a false attack because he was actually one of the major supporters of the paper, but he thought that the technique was too general to be a computer vision paper. And now I'm just going to show you why. So you can actually use this to essentially perform some soft version of ransack. So for example, if you train it to perform robust fitting with respect to some outliers, you can actually show that as you're going deeper within the network, basically the same thing that will happen in NRLS will be happening. So you're going to lock in progressively to a solution, and it works really, really well from that point of view. You can use it to, you can use the normalization layer to make shape classification or point cloud classification much more robust to outliers. And don't be fooled about outliers as just being uniform outliers. If you have, if you cut out with a bounding box an object within a scene, a chunk of an object that doesn't belong within the bounding box is also an outlier, right? So we have evidence in the past that that was also the case. So it's both uniform outliers, but I'm pretty sure that, or quite confident that this will apply also to foreign objects that appear within the bounding box of something else. And the canonical or the major application that we looked at was actually wide baseline stereo, where again, we have this set of putative correspondences that exist in between two images. And this simple normalization layer that was allowed to refine an hypothesis as you go deeper within the network was actually able to achieve state-of-the-art in this application. And I want to say, as usual, like, you know, it was state-of-the-art at the submission time for CVPR last year. And of course, it was not state-of-the-art anymore, but our colleagues are actually running a benchmark for wide baseline stereo at this CVPR. And it turns out that the submissions to the benchmark now include attentive context normalization as one of the components within their bigger ecosystem. So maybe the ACNe network is not anymore state-of-the-art, but the ACN block still is, because it's actually part of other solutions that we know, at least
Andrea,
for now.
I have
Yes.
a quick question. So
yes.
I'm wondering, like, for instance, for this particular problem, what is the input features actually? So what is the information that is used by the network to determine the weights? Is this information also about local descript, like the local region?
You can put in whatever you want. Yeah, you can put in whatever you want in the network. So if it's kind of like what PointNet was doing, right? You can use just raw points, and that will be fine. You can introduce local features and you just concatenate them and it will be fine as well. So it's extremely general from that point.
Yeah, but for
could be anything.
For this feature, wide baseline feature matching problem, I assume you somehow need to also input the putative correspondence information somehow, no?
Local descriptor, yeah, like the stuff that Kwang was doing, yes.
Okay.
Yes. So there is some form of like local geometry of the scene also included within the point. That's actually a very good point. I should have asked Wei to also run it without descriptors, because I'm pretty sure you will still get something very reasonable, just because it will consensualize all of the geometry within the problem quite well. Because that's exactly what happens, for example, in the line fitting problem, right? It doesn't have any form of descriptor, but it's still able to lock in the solution just because it makes sense in a global aggregation point of view. But yeah, that's a very good. I'm actually going to ask Wei to run that experiment, and I'm pretty sure the numbers will not be as good as the one that we report here, but I'm pretty sure it will still work to a large degree.
I mean, one difference to the single point set experiment is that here you have 2 point sets, right? So you need to somehow find features that take into account both point sets, not just one point set, in a somehow equivariant manner, I assume, no?
Yes. Yes.
So another question, if there's time, do I get it that you have to have an initial guess?
So this is actually a very interesting question. For this paper, we kind of wanted to have a deterministic output, and that's why if I scroll back to this slide, essentially this first block over here has the role of generating the first version of the optima that you want to, or the first version of the features that you would like to use. But in fact, I think that if you replace this block with a randomized search that proposes multiple potential starting points, these will actually be, it will be allowed to basically generate even a multimodal solution space where few of them might converge to different modes that the network was able to find. So for example, if you think things like symmetry, this should be able to find out 2 solutions in symmetric sets, right? So if you have a picture of a building and you can flip it along the main axis, then there is two potential solutions, and this should be able to lock in. But this is not something that we looked into in detail. We just we wanted to have something simple and straight that just gives you one solution all the time, and then we just went with that. But that's a very, very good question. And this actually, I think there is a way of writing all sort of multimodal problems leveraging this trick, and it's something I've been trying to convince people to work on, but I've not started anything in regards yet.
Okay, thanks.
No worries. 9:23. I'm being a bit slow. So the second, oops. So let me just do so just a summary of the first of the three things that I wanted to talk about. So we basically create a network that is inspired by RLS. Internal is essentially an attention model that decides which features and how to update the features in such a way that it is able to solve the final problem. You can take the whole network, or you can just take the normalization layer. And I swear, if you have a point problem, plug it in, and you're going to get a few percentage boost to your performance, because we allow the network to reason about outliers. We get state of the art weight baseline stereo, and we also get, as some internal test, we actually get state of the art as well in point-based reconstruction. But this is something we're working right now in Victoria with Wei. And it's basically a multi-headed attention model based on ACNe. That's basically the short story. So the second, so this is it for the first problem. As I said, it was about parsing the scene. The second part is about reconstructing the scene, and in particular, reconstructing humans, which are kind of important for computer vision. And I'm going to introduce neural articulated shape approximation, right? So what I mean by that, and this is a joint work with Boyang, JP, Timothy, Gerard, Jeff, and Mohammed. What I mean by this is that if you look at the way in which people typically model digital human, and we have Michael on the call, so he's the leading expert in regards, is that this is the kind of pipeline that you have, right? So you're going to have a control rig, which is designed by an artist on the left. You're going to have a mesh, which is beautifully designed by an artist on the right. And this mesh is controlled by some deformation parameter theta, maybe by some shape parameter beta, but we didn't cover that part in this work. And then you're going to have some differentiable skinning operation that is controlled by skinning weights, which are, again, are artist generated, right? And now, you know, Michael has actually shown this paper at CVPR this year, where they were starting to care about the interaction of humans with the environment, where maybe collisions and interpenetrations start to become important. And now, as soon as you do that with meshes, you're going to need some operation that is able to convert a surface model into a volumetric model to be able to answer things like collisions and interactions and so on, right? So you're going to now rely on some potentially data structure, which might be difficult to actually differentiate through, that converts a surface model into a volumetric model that expresses occupancy, right? So this is a function. You plug in a point, you plug in the pose of your model, and it tells you whether that point is inside or outside of your human, okay? And what we did in this project is actually kind of rewrite the entire pipeline from scratch. We said, okay, we don't want to have man-made stuff. So we're assuming that the pose representation is just a collection of coordinate frames. It's like basically a set of these little transformations here on the left. We assume that the element in the middle is just a bunch, it's just a network, so it's just a bunch of MLP. And what we want on the right is directly this sense of this measure of occupancy, right? So we don't want any mesh that when we have to post-process. So we want a function in output so that we're able to perform queries against this function. And again, this function is just an occupancy. It means that it's positive inside of the object and negative, sorry, less than 0.55 outside. And the 0.5 transition is at the boundary of the object. So this is just a cross-section of the function. So how do we do this? So the first thing that you could do is that you could try the ACNet, DeepSDF, and IMNet version of this. What you could do is that you could find a way of encoding the pose, and this might be the SMPL, the simple pose parameters, for example. And you could use that as conditioning of an MLP that, given a position, will tell you whether that point was inside or outside of the object, right? So this is a straightforward extension of ACNet and similar architectures. So this is the first variant. The second variant that you might do is like saying, well, if you look at the way in which human bodies and even skinning, for example, is computed, that typically you have coordinate frames and you have parts of the body that make the whole, right? So you could say, okay, now I'm going to use an ACNet like structure for each of the coordinate frames that have an input, And I'm also going to provide each of them with the local coordinate frame of the query point. It turns out that MLPs are pretty bad at computing dot products. So change of coordinate frames rely on dot products. So if you allow the network this bit of freedom, it learns a lot better, by the way, if you want to test my hypothesis out. And this will give you a rigid composition of the body, right? So because each of these MLPs is unconditional with respect to the pose, so it will be a rigid decomposition controlled by the coordinate frames that gives you the human body by taking the union of all these rigid parts. And then the third variant is actually pretty similar to the one you have right now. You add these extra branch where these ACNets are actually now given not just the pose, right? But you're giving a subspace projection of the pose. And why this is important is because, you know, if you consider your bicep, the geometry of your bicep only changes with respect to the degrees of freedom that correlate the position of your forearm to the position of your upper arm, right? So you don't need the entire body pose to determine the geometry of your bicep. So that's what this linear projection actually is doing, is localizing the pose vector to what is important for this particular unit. So what happens if you do this? You can use the AMASS dataset. Thank you, Michael. That saved my life when you released the dataset. And thank you, Gerard, for making my life easy in being able to use it. So you can compare the U network, which is basically ACNet, where you just feed this pose parameter and input, to the rigid model, to the deformable model, right? So the D model is essentially, it's kind of like simple. It has these way of deforming these implicit functions according to pose, which is like the blind shape corrective model. And if you see actually the change in performance, more or less along all metrics, you see that the improvement in performance is drastic. Not just a little bit, is actually up to like 50% change absolute in performance, right? So this is a reconstruction task. We're just basically trying to say, given the pose parameter, please reconstruct the occupancy given this pose. And we use two different parts of the AMASS dataset. We use the defaust, which basically verifies that the model works across different identities, although you're overfitting to a particular person, but it works for different people. That was the point. And then we use the transition dataset that has only one person, but a lot more movements. So it's a lot more difficult to extrapolate. And you can see that, for example, even in terms of IOU, again, you get roughly a 50% gain in performance. So it's quite drastic. So this is great. It means that, you know, if you're trying to represent humans with MLPs, and if you're trying to represent systems that include the concept of coordinate frames, that you really should be encoding them directly within the network. But what we do on top of this just simple reconstruction task is just saying, okay, now we have a new representation. Can we use it for some of the classical tasks? And one of the classical tasks that we took is deformable registration, right? So potentially, I don't see the full list of people, but potentially many of you, Michael for sure, knows how painful it is to implement this optimization. So basically, this is what MOSH or the original Simple was doing. So this is basically what generates deformable models for Simple, right? So phi is the sign distance function, and D could be a depth map or a point cloud. And you're basically trying to make sure that the point X in the point cloud lie on the surface of the object. And you're trying to find out the pose of the object so that the object aligns to the point cloud. And what we show in this paper is that actually you can actually use neural networks directly to perform this operation. I'm not going to go through the derivations, but you're going to take this equation. You're going to do a first reparameterization, basically the sign distance by splitting an occupancy with a Gaussian. And then it turns out you get to, after a couple of steps, you get to this expression. And what this allows you to do is what you're seeing in this video right here. So this is the ground truth mesh. This is actually a neural network. It's not a mesh anymore. It's just being visualized by marching cubes. And basically, this neural network is tracking this point cloud. This is not machine learning, right? I'm using a deformable model that was learned by a neural network to track a point cloud. So this is pure optimization. I'm optimizing this thing on the right, right? So there is no, these are not network parameters. These are pose parameters. And if you see the expression of the optimization, the only thing you need to access is the occupancy function, nothing else. And the only complication in the operation is differentiating with respect to an expectation with respect to a Gaussian sampling around the point. So it's super simple, right? And that's what I mean by closest point free ICP registration or deformable ICP. It means that you can actually implement this deformable tracker in few lines of TensorFlow code, without any complications at all, which I think is a first. I don't think this existed in the field. Correct me if I'm wrong, but the closest thing to is was the autodecoder from DeepSTF, but that's a slightly different problem. All right, so this is the summary of NASA. Let me check how I'm doing in time. Okay, now I'm doing pretty good, and I lost my auxiliary Zoom window.
Maybe I can ask a question. So,
yeah.
like, what is the level of supervision that is required? I mean, is this just a set of point clouds, or do you need more supervision?
That's an excellent question. So what we're doing is that we're using the same supervision that ACNe was asking. So we're using occupancy supervision. So we randomly scatter points on the surface and outside. However, we were working on this in parallel to when sign agnostic learning popped up. So and we didn't work on this further, but with a fair amount of confidence, I can say that if we replace the occupancy supervision with a SAL-like loss, we can actually just work in the reconstruction task with just surface samples. And this is not something that we're working on right now, but I'm with a pretty high degree of confidence, I'm sure you can do that. Also, what you could do is that you could use a multi-view stereo kind of acquisition, like the one that Michael has in his lab. You could take the dense point cloud sampling the body, you could pass it through something like generalized winding numbers, and that will give you an occupancy. And then you can use that occupancy function to train the system. So you can still train it. So if your point cloud is relatively dense, rather than using SAL, you could use generalized winding numbers, and you will get the occupancy that you want.
But you don't need any supervision on these little coordinate systems that you show here on the slide. So these are all.
We are providing supervision on that as well. So here in this case, we were trying to see, okay, if I give it the same level of supervision that mesh models have, how well do implicit models perform? And the answer was terrible, which was these stats that we have collected over here on the right.
Yeah,
which means that there was something really broken.
Just quickly ask, like, how these coordinate systems are defined? Are they basically related to joints of the human body or to angles?
Yeah, so what we did is that we just took the coordinate frames, we decoded the absolute coordinate frames from the simple model, and we just fed those in input to the network.
Thanks.
Yeah. And something else also, once you do this parameterization, the model becomes completely translational equivariant, right? Because whenever you perform a query, if you notice over here, your query point gets written in the coordinate frame of the current state. So that means that the network doesn't care about where the query points are located in the environment, because it factors out basically transformations at the input layer. So there's no assumption that the human body lies in the origin and is normalized to unit. It doesn't care, right? Because all of the information is factored out as soon as you enter the network. Any other question on this?
I had a quick question. So you started motivating that by saying this is a great alternative to AAB trees. Do you have any numbers on how fast is the query of the NASA network compared to an efficient implementation of an AAB tree on the GPU?
Right. I have numbers in terms of number of queries per second. It's in my rebuttal. I will have to open up my other machine and look it up. So if you ping me after the talk, I think it was 10 million points per second. But I will have to look it up. I don't have that number written. It's in our rebuttal. So it's, yeah, just ask me later and I can tell you. But the thought is that, these are just simple MLPs, and this is just the first version of the system. And from other parts of computer vision, we know that the training version of networks are heavily overparameterized, and you can get enormous speed ups in performance. So the idea was like, okay, let's try to explore the problem from this new point of view, and any advance in making network more efficient will be able to use them. Does it make sense? Hello?
Yes, it does. Thanks.
So we didn't look at it from the efficiency point of view, but we're saying basically that because it's just a forward propagation step, we can. And there is a lot of work that is happening in neural networks to make them faster. So it's not the emphasis that we wanted to focus on. And of course, right now it's limited to a single subject, right? So we overfit to a single parameter beta in the simple lingo. And clearly an extension of this will just be, okay, now what happens if we also want to model cross-human transitions, or what if we want to have a model that respects for example, the facial details with more fidelity and things like that. But those are additional questions you might ask.
Right,
so this is the,
I have another question. So if, say you had, sorry to interrupt your talk like that, but if you had the registration looking back, so the subject has a rotation of 180 degrees.
Yes.
The NASA representation would still fit him or her fine. They're just rotated.
Yes.
Is that true? So would you be able to, if your initial rotation of NASA is frontal looking, you'd still fit them?
So think of NASA as being a replacement for surface meshes, right? Like, and then you can answer the same question from what you might know from registration with surface meshes. If I give you you facing forward, but I give you an initialization of you facing backward, a local optimizer like ICP will register to the wrong local minima, right? So it doesn't, it's just an alternative to surface meshes.
But for a surface mesh, I could say like initial, so I have like landmarks, so I know like the face is parameterized by indices. So I can say that actually the face, that point on the mesh should be here, but on the NASA, I don't see how I could do that. If I'm wrong.
It's exactly the same, because the parameters theta's, disposed parameters decode to a collection of coordinate frames, and you can simply impose constraints on the coordinate frames. So it's literally identical to meshes in the way in which you will achieve this.
Okay.
In fact, actually, we have one of the classical priors, which was like bone length, inserted in the tracking application, and we were able to make it work quite well. So it's completely compatible with anything that you are doing on the surface mesh kind of ecosystem.
Andrea, quick question. How does the shape parameter is used? Like, I only see the implicit like surface function being deformed by the pose parameters. Is there a way to control also the shape betas?
So we did. I mentioned it in this slide. Like currently we're limited to single subject. You could. It's just we didn't look into it.
Sorry. Yeah. Cool. Thanks.
Yeah. So I am pretty sure that this will generalize also to that. There is no reason to believe that it will not. And it's just that we didn't run that experiment because we had enough meat in the paper and we're running out of space actually. So it's as it happens in this case. But yeah, you could definitely try, and I'm with a high degree of confidence I can tell you that it will work. So the third thing that I wanted to talk about was ConvexNet. I'm not going to talk about BSPNet, the award paper, because you can see it as being an extension of ConvexNet, and also it's heavily related, so you can actually understand the difference once I explain this version. So for ConvexNet, we wanted to ask the question like, what is the best 3D representation, right? And if you look at the field, there is essentially like two classes of methods. There is the one that work on traditional explicit representations, like triangle meshes and soups and point clouds, which are great for doing inference because you generate something that computer graphics is familiar with, but they're a bit more painful for training, especially in the case of triangle meshes. You're going to have to determine the triangulation, which is a combinatorial problem, which, as you know, networks have a bit of a problem working with. And on the other hand, Andreas, I guess, is one of the experts in this area. You could use implicit functions. And for unconstrained learning, where you do not know the geometry that you're about to reconstruct, this is great because the topology can be updated at training time, right? So the surface is built at training time, or the topology of the surface is built at training time. However, the inference is a bit painful because you're going to have to run marching cubes to extract the surface. And this can take up to the order of seconds to compute the surfaces to a high degree of accuracy. And what we wanted to do is that we wanted to kind of like merge these two fields. And I guess Michael knows that I've been looking at hybrid representations for a while, with like sphere meshes and other things. So we wanted to kind of merge these two ecosystems in something that was working quite well. And what we did is that we actually went into the realm of convexes. So why convexes are important? Well, in traditional graphics, convexes are actually universal approximators of geometry, which means they do not only give you a rough approximation that can be used for things like physics, but if I increase the number of convexes that I use, actually this is not infinity, but I might need infinitely many for an infinitely smooth surface. you can actually generate exactly the same surface representation that you have in input, right? So they're universal approximators from that point of view. And the other thing that is interesting, if you open up any commercial or open source tools for working with graphics and rendering, you open up the rigid body physics module, and you typically get this drop-down list. And as you can see, as you go down, the models become more and more complex, and the last two entries are convex hull and meshes. And if you run things on convex hulls, like PyBullet, basically the default solver for PyBullet is based on convexes, and the next stage is meshes. And I would invite you to try to do a simple rigid body dynamics with the raw meshes and the mesh accelerator, and it will break basically immediately. So the last entry is to be used with a lot of care. It's basically the Wild West. And the idea is that, okay, we have these universal approximator of convex domains. And the interesting thing is that convexes can be dealt with by neural networks much easier than, in a much easier way than meshes can. So why? Well, first of all, convexes can actually be written as a collection of half spaces. So you can have a half space tensor, as you can see right here. Each line corresponds to a half space equation. And this is essentially the visual representation, right? So here I have 5 half space tensors. Each line represents a line and a discard area, right? So it's an oriented line that tells you which parts of the volume to discard. And what it turns out is that I can take this collection, this tensor of half spaces, and I can actually generate an implicit function out of it, right? So, and this is this differential module C, and the equation of C is actually super simple, right? That's it. That's the only thing you need to know. You spit out this tensor and it generates a function, like in the ACNe sense, right? So it trains in the ACNe sense. And the parameters of these functions, like, you know, as, of course, because it's a collection of, it's a set of tensors, is invariant to the ordering of the rows, although we didn't leverage this process in training. And then you have parameters that control like the smoothness of the boundary, as you can see right here. Even though you have only 5 equations, you can actually get very smooth boundaries, or the smoothness of the transition in such a way that gradients can propagate a lot easier through the system. And the cool thing is that because we're working in functional space, we can simply say, okay, do not only predict the parameters, these hyperplane parameters beta that determine the shape of the convex, but also predict the transformation that places this convex somewhere in the environment in such a way that when I take a union, so when I take the max of the occupancy function, I can actually also reconstruct non-convex shapes. And the cool thing is that you can take this recipe, and as you know, ACNeX generalize almost transparently from 2D to 3D, which means that you can actually now obtain the compositions of 3D objects like you see right here, where each of the component is a convex, and together they reconstruct the full shape, right? So the training, I guess you got, this group is one of the experts in this particular field. The training basically essentially leverages the fundamental loss, basically compares occupancies in between the two models. So you just sample the prediction, sample the ground truth, and make sure that they agree with each other. And there is a couple of auxiliary losses that we prove why they are necessary for this optimization to help the convergence. But what is interesting about this model is that while training happens at the implicit level by decoding a tensor of half spaces into an implicit function, at inference time is actually a polygonal mesh. Why? Because as you can see, my tensor produced by my encoder could be something like this, which is the tensor of equation I showed you earlier. And what I can do is that I can convert these set of hyperplanes or half spaces into a collection of points by taking the duality transformation in between point and lines. I can compute the convex hull of these points in dual space, and now obtain these green edges E, okay? And now I can take a second duality transform that maps point to lines and lines to points to go back to the original space. And these edges E will become these points E subset, whatever they were connecting. And now if I take a second convex hull operation, I obtain a polygonal mesh. In this case, it is a polygonal boundary or convex polygonal boundary. And this actually, of course, works straight out of the box in 3D as well. I can take now an image encoder. I can concatenate it with a convex decoder. And now I obtain the smooth function during training, but I also obtain similarly the polygonal function at testing time. And I don't need to run any marching cube to generate this polygonal function. It's a polygonal function by design. And because it's a polygonal function made of convexes, I can feed it to PyBullet and I love this little video because it's entertaining. I can basically run simulations straight out of the box without any need for extra conversions in between the models. And of course, this is just a differentiable decoder. You can plug it in with respect to any differentiable renderer model that you have, with respect to any differentiable physics solver that you might have, and so on, right? So it's and of course, the quality of the encoding depends on the encoder side of things, right? So it will improve in performance as the encoders become more sophisticated. So as I said, like there was this other piece of work that I did with my my alma mater at SFU, which was called DSPNet, and the version that I showed you right now basically describes an object as a collection of k-convexes, and each of these k-convexes had h hyperplanes, and these two quantities were fixed. So always use k-convexes, always use h hyperplanes. And what we did in this follow-up work, which was presented at the same time at CVPR, but it was a follow-up work, we said, okay, now can we find a way of learning basically how to spend your hyperplanes? So we're going to give you 5,000 hyperplanes to use, and during training, you're going to decide how to spend the hyperplanes on which of the convexes. And what this does is that, as you can see, the network can decide, for example, not to use one of the convexes, right? And maybe only use a much smaller number of convexes than the previous version of the algorithm was using. And I think this is actually, from what I know at least, is the cleanest way of getting a variable cardinality output from a network that I've found. And it's basically exploiting some of the structures of convex polytopes to do this. All right, I think that's it. So just a recap on this part. So we introduced a differentiable layer for a differentiable decoder layer for convexes, right? So you can use it for whatever you want. It's a hybrid representation because it trains as an implicit function, but it evaluates as a polygonal mesh. The polygonal meshes you get in output are simulation ready, so you can plug them into differentiable rendering and differentiable physics if you want to do so. They also, because they're convexes, they also admit parametrization, right? Because they're homotopic to a sphere, so you can put textures on them if you want from a differentiable rendering point of view. It achieves state-of-the-art reconstruction on some classes of problems, and is comparable to OCNETs and similar methods on single view reconstruction. And it enables potential applications, as I said, on rendering and physics, but we're not looked at that time yet. And the source code for it is actually, for both ConvexNet and BSPNet, is already public. So just a recap. So basically, I showed you these three components, like how to parse scenes. So this is more on the encoder side, by using an attention model that is inspired by IRLS. I then show you how to encode humans in a different way from what was done historically, by having a representation that is learned completely end-to-end. And finally, I showed you a representation that allows you to have a training regime that is much more friendlier to neural networks, while at the same time having an output regime that is much friendlier to computer graphics and traditional applications. So these are the three works that I wanted to show you. These are kind of old now because they're back from November. We have a bunch of different new works, not exactly in these areas. We have one that I'm particularly fond of that is not quite ready, which is VoroNet, which will extend these methods to produce actually watertight polygonal meshes in a single shot rather than a collection of components, but it's not quite ready. So it's still work in progress on the front. And, you know, at Google Brain, we're actually very free to collaborate with other groups. So if you guys are interested in extensions of these methods, just shout out, and I'm more than happy to talk and discuss about where to go next. All right, that's it.
That's first.
That's all I have to say.
Thank you very much. It was a fantastic presentation. Thanks.